3.8 Lesson 2, Applications of Sine and Cosine Derivatives. Our objectives for today are you'll be able to sketch graphs of functions that are transformations of the parent sine and cosine functions. So a transformation of a parent sine or cosine function would have this form where a, b, c, and d are called parameters, and b times x minus d is called the argument of the cosine or the sine function. And the values of the parameters a, b, c, and d, the value of the parameter a will tell us what the amplitude of the graph is. The value of the parameter b will tell us about a horizontal stretch or compression. It will also tell us about the period. The period will be 2 pi divided by the absolute value of b. The value of the parameter c will tell us about a vertical translation, and it will tell us also the midline axis or the sinusoidal axis. And the sinusoidal axis will be a horizontal line having the equation y is equal to c. And the value of the parameter d will tell us about a horizontal translation, also called a phase displacement. So for a given graph of a transformed sine or cosine function, y is equal to c plus a times cosine or sine of b times x minus d, you'll be able to identify the amplitude of the graph, which is related to the parameter a. You'll be able to identify the period, which is the period of the function is 2 pi divided by the absolute value of the parameter b. The equation of the midline axis is y is equal to the parameter c, which gives us a vertical translation, and the phase displacement is equal to the parameter d. The phase displacement is also called a horizontal translation. You will also understand how the parameters a, b, c, and d affect each of the above, and we just went over that. The parameter a tells you the amplitude of the graph. You can use the parameter b to find the period of the function as follows. The parameter c tells you the equation of the midline axis because it gives you a vertical translation, and the parameter d gives you a phase displacement. The parameter a also tells you about the vertical stretch or compression that you have. The parameter b tells you about a horizontal stretch or compression that you have. Once again, what do we mean by the argument? The argument is what we're taking cosine or sine of. In what I have here, it would be b times x minus d. Here we have a summary of what we just discussed. If you have a function of the form y is equal to c plus a times cosine of b times x minus d, or it could be sine as well. This is called the general equation of a sinusoidal function, and a, b, c, and d are called the parameters, and as we discussed, the parameter c will give you a vertical translation, and the midline axis or the sinusoidal axis will be the line y is equal to c. The parameter a will give you a vertical stretch or a vertical compression, and the amplitude of the graph will be the absolute value of the parameter a. 1 over b is the horizontal dilation factor. It will be either a horizontal stretch or a horizontal compression of the parent function's graph, and the period will be 2 pi divided by the absolute value of b. And the parameter d will give you a horizontal translation, giving you a phase displacement. So number 1, we have y is equal to 3 plus 2 times sine of 2 theta minus pi over 4. Here is what we would like to do. We would like to sketch the graph of the function, and then once we have the graph, We'd like to identify its amplitude, the period of the function, the equation of the midline axis, and the phase displacement. The first thing that we'd like to do is to recognize that the argument of our sine function is 2 theta minus pi over 4. That's the argument of our sine function. The next thing that we'd like to do is identify the values of the parameters a, b, c, and d. So we can see that the parameter a is 2. We can also see that the parameter c is 3. However, when it comes to the parameters b and d, to identify the values of these two parameters correctly, the argument must be written in the form b times the quantity x minus d. So as you can see with number 1, the argument is not quite in that form. So what I can do is recognize what the form entails. First of all, whatever the variable is, whether it's theta or x, in the quantity x minus d, you have to have 1x minus d, or 1 theta minus d. So right now you see that there is a factor of 2 multiplying the theta. So you don't want that. You want a 1 there. So here's what you need to do. You need to go ahead and factor out 2 from the quantity 2 theta minus pi over 4. So this is still in the argument, but now I factor out, so this is still the argument. So I'm just going to write the argument in a different form. I factor out 2 from the quantity 2 theta minus pi over 4. So when I do that, I will have 1 theta minus pi over 8. If you distribute the 2 back into the quantity theta minus pi over 8, you will get 2 theta minus 2 pi over 8, which is of course pi over 4. And I put 2 times theta minus pi over 8 in green parentheses just so you understand that that is the argument of the sine function. One way to sketch a graph of this transformed sine function is to make a table of values. Another way to sketch the graph of this transformed sine function is to start with the parent sine function and apply the individual transformations due to each of the 4 parameters. For example, you could start with the parent sine function, you could do a vertical stretch, you could do a horizontal compression, you could do a vertical translation and a horizontal translation to get the graph of the transformed function. And a third alternative is to look at coordinates of points on the graph of the parent sine function and use coordinate notation for transformations and find corresponding coordinates on the graph of the transformed function. We'll take a look at the first 2 ways of doing this. So the first way is to make a table of values. When you make a table of values, your table should have 3 columns. The middle column will be the argument of the function. What is the argument? It is what you're taking sine of. And you want to choose the argument to be the quadrant angles, 0, pi over 2, pi, 3 pi over 2, and 2 pi, because it is easy to evaluate the sine function at these 4 quadrant angles. Sine of theta is simply the y-coordinate of the intercepted point on the unit circle. So we choose the argument to be 0, pi over 2, pi, 3 pi over 2, and 2 pi. And we can then do the following to find what the output values of the function should be. So these are the output values from the function, y. But what would be the input values? It would be theta. The middle column is not input values. The middle column are values for the argument. But you have to work backwards to figure out what the input values are that would give you these values in the middle column for the argument. And we will get to that towards the end of working on the table. But what we want to do first is work with the arguments that we've chosen, because these are the quadrant angles. It's easy to evaluate sine at these 5 values for the argument. So sine of 0 is 0. The next thing that you do is 2 times sine of 0. So you have 2 times 0, which is 0, and then you add 3. So 0 plus 3 will give you 3. What is the sine of pi over 2? Sine of pi over 2 is 1, and then you do 2 times 1, which is 2, and 2 plus 3 is 5. And then you look at the argument pi. Sine of pi is 0. You do 2 times 0, which is 0, plus 3 is 3. And then you look at the argument 3 pi over 2. Sine of 3 pi over 2 is negative 1. 2 times negative 1 is negative 2. Negative 2 plus 3 is 1. And then you look at the argument 2 pi. You do sine of 2 pi, which is 0. And then you do 2 times sine of 2 pi. 2 times 0 is 0. And then you do plus 3, which gives you 3. So these are output values from my function that I have in the third column. The middle column are values of the argument. The first column are input values, because when I plot points, I need input, comma, output. So I need to figure out what input values will give me 0, pi over 2, pi, 3 pi over 2, and 2 pi for the argument. And it's easy to figure that out. All you have to do is take 2 times theta minus pi over 8, which is your argument, and you're setting that equal to 0 in the first case. You're setting that equal to pi over 2 for the second row. You're setting it equal to pi for the third row. You're setting it equal to 3 pi over 2 for the fourth row and 2 pi for the fifth row. And you need to solve for theta in each of these 5 equations. But actually you can do about 3 of them, notice a pattern, and then apply the pattern to figure out what the inputs should be for the fourth and the fifth rows. So if I divide both sides of the equation here, for the first equation, by 2, I will get theta minus pi over 8. 0 divided by 2 is 0. And then I can solve for theta. I get theta is equal to pi over 8. So I get pi over 8 for my first input. If I multiply both sides of the second equation by 1/2, 2 times 1/2 is 1, so I get theta minus pi over 8 is equal to pi over 4 on the right side. Add pi over 8 to both sides of the equation. You can write pi over 4 as 2 pi over 8. So you have plus pi over 8. So that will give you 3 pi over 8. So the input for the second row would be 3 pi over 8. And for the third row, I will solve the equation here that I have here. I can multiply both sides of the equation by 1/2. On the left side of the equation, I will be left with theta minus pi over 8. On the right side of the equation, I'll have pi over 2. And then I can add pi over 8 to both sides of the equation, and that would give me theta is equal to pi over 2 would be the same as 4 pi over 8. 4 pi over 8 reduces to pi over 2, and then I can add pi over 8 to that, and that gives me 5 pi over 8. By now you might notice a pattern. You go from pi over 8 to 3 pi over 8 to 5 pi over 8. So each time the numerator is increasing by 2 pi. So the next row should have an input of 7 pi over 8. And the last row should have an input of 9 pi over 8. So we have 7 pi over 8, and we have 9 pi over 8. So now I have enough to be able to plot points that will be on the graph of my function. And my points are going to be, my ordered pairs are going to be pi over 8, 3, 3 pi over 8, 5, 5 pi over 8, 3, 7 pi over 8, 1, and 9 pi over 8, 3. So I need to take these 5 ordered pairs and plot them. I've written just the first couple of them as ordered pairs, but you know what the other 3 are. We just went over that. So now how do we plot these ordered pairs? Well, if you look at your horizontal axis, that's your theta axis. So we have theta on the horizontal axis, and we have y on the vertical axis. So you need to find where pi over 8 is. Well, here's pi over 2. So half of pi over 2 is pi over 4, and then you have half of that, which would be pi over 8. So what I've done is I put some red points on the horizontal axis, and I put a red point at every eighth of pi. So the first red point that you see here is representing 1/8 of pi. So I have 1/8 of pi, 3. And then I have 3 pi over 8, which is 3/8 of pi, 5. And then I have 5 pi over 8, which is 5/8 of pi, 3. And then I have 7 pi over 8, which is 7/8 of pi, 1. And then I have 9 pi over 8, which is 9/8 of pi, which is 1 and 1/8 pi. So 1 pi plus 1/8, and then I have 3. So what I have here is one cycle of the graph of y is equal to 3 plus 2 times sine of 2 times theta minus pi over 8. Of course, I can continue to graph additional cycles. And you can see that I've added 3 additional cycles to the graph. So we just sketched the graph of a transformation of the parent sine function. So we accomplished objective 1. And now we'd like to take a look at objective 2. For a given graph of a transformed sine or cosine function, let's identify the amplitude, the period, the equation of the midline axis, and the phase displacement. You will also understand how the parameters a, b, c, and d affect each of the above. So the parameter a, the absolute value of the parameter a, will tell us the amplitude. 2 pi divided by the absolute value of the parameter b will tell us the period of the function. The parameter c, the equation y is equal to c, will give us the sinusoidal axis or the midline axis. And the parameter d will give us a phase displacement from the parent sine function. So for our function, the parameter a is equal to 2. The parameter b is also equal to 2. And I was able to tell that the parameter A was equal to 2 just by looking. A is equal to 2. The parameter B is equal to 2. The parameter C is equal to 3. And the parameter D is equal to pi over 8. So, because of that, I know the following. I know that the sinusoidal or the midline axis is the line y is equal to c. So c is equal to 3, so the line y is equal to 3. This line y is equal to 3 is called the midline axis or the sinusoidal axis. I know the amplitude is equal to the absolute value of A. The absolute value of 2 is 2, and the amplitude is 2. And what do we mean by the amplitude? It is the distance from the midline axis to either a high point or a low point. So you can take a look over here. This would be the amplitude. The amplitude is 2. Amplitude is 2. The absolute value of 2 is 2. I know the period is equal to 2 pi, which is the period of the parent sine function, divided by the absolute value of the parameter b. So I will have period is equal to 2 pi divided by 2, which is 1 pi. And you can see the period here. If you look at, for example, one cycle of the graph, for example, look at the cycle that's shown in red marker. If you look at the cycle that's shown in red, that cycle starts at theta is equal to pi over 8, and it ends at theta is equal to 9 pi over 8. 9 pi over 8 minus 1 pi over 8 is 8 pi over 8, which is, of course, 1 pi. So that's the period. The period is 1 pi. So we looked at the sinusoidal axis, we looked at the amplitude, we looked at the period, and now the phase displacement is equal to the parameter d. The phase displacement would be equal to pi over 8. And what does that mean in the context of this problem? What does it mean that the phase displacement is equal to pi over 8? To help you understand what we mean by phase displacement is pi over 8, let's look at the graph of the parent sine function. F of theta is equal to sine of theta, which I will show in blue. We know sine of 0 is 0, sine of pi over 2 is 1, sine of pi is 0, sine of 3 pi over 2 is negative 1, and sine of 2 pi is 0. So you can see that this cycle of the sine graph starts at 0, 0, where the input value is 0. And if you look at the red cycle shown on the graph of our function that we just graphed, you can see that the red cycle starts at pi over 8 for the input value, and the output value is 3. So you can see that each cycle of the sine wave starts at a point that is on the midline axis. And for the parent sine function, this cycle closest to the origin starts at input value equal to 0, but for our function, our cycle starts at input value equal to pi over 8. So there has been a horizontal shift to the right by pi over 8, and that is what we mean by the phase displacement. And of course, you can visually see that we also have a vertical translation upward by 3 units due to the parameter c. And the way you can see that is that for the parent sine function, The midline axis is the line y is equal to 0, and that's been shifted up by 3 units. You can also see that the amplitude has changed. For the parent sine function, the amplitude is 1. The distance between the midline axis and a high point or a low point is 1 for the parent sine function. But for our function, the amplitude is 2, and that's due to the parameter a equal to 2. And you can see that for the parent sine function, the period is 2 pi, but for our function, you can see that the period is 1 pi. There's been a horizontal compression by a factor of 1/2, and that's due to the parameter b being equal to 2. So the period will be 2 pi divided by 2, and the period of our function for number 1 is 1 pi, whereas the period of the parent sine function is 2 pi. So that's how you can relate how the parameters are affecting each of those quantities. The amplitude, the period, the sinusoidal axis, and the phase displacement. So today we looked at sketching graphs of functions that are transformations of either the parent sine or the cosine function. And after you sketch the graph, for a given graph of a transformed sine or cosine function, we identified the amplitude, the period, the equation of the midline axis, and the phase displacement. And we related those to the parameters a, b, and c, a, b, c, and d. We'd like to conclude the lesson for today by showing you an alternative way you can get the graph of the function from number 1. In this alternative way, we're going to start with the graph of the parent sine function. F of theta is equal to sine of theta. So we have sine of 0 is 0, sine of pi over 2 is 1, sine of pi is 0, sine of 3 pi over 2 is negative 1, and sine of 2 pi is 0. So here we have the graph of the parent sine function. We have one cycle of the graph. The period is 2 pi. The amplitude is 1. The midline axis is y is equal to 0. And let's go ahead and take a look at how we can get the graph of number 1 by using the values of the parameters a, b, and c, and knowing the transformations we get for each one of them. So we will begin with the parameter b. Actually, I'd like to correct myself. I said we will begin with the parameter b, but it's actually easier than that. We will just go a, b, c, and d. So we will begin with the parameter a, we'll go to the parameter b, we'll go to the parameter c, and we'll end with the parameter d. A, B, C, D, 1, 2, 3, 4. So we will apply these transformations in the order of A, B, C, and D, 1, 2, 3, 4. So the parameter A, and here we have the parameter A, here we have the parameter B, here we have the parameter C, and here we have the parameter D. A, B, C, D, 1, 2, 3, 4. So the first parameter is A, and A is equal to 2. And what does A tell us? A vertical stretch or a vertical compression. So because A is equal to 2, we will have a vertical stretch of the parent sine function's graph by a factor of 2. So what that means is, when you take a look at this point, pi over 2, 1, it will become pi over 2, 2, because you multiply the y coordinates by A, by 2. So this point here, 3 pi over 2 negative 1 will become 3 pi over 2 negative 2. Points that have 0 y coordinates, 0 times 2 is still 0, so they stay the same. So the first transformation that I apply is for the parameter A, and that gives me this graph. But of course, this is not my final graph. Now I have to apply the transformation due to the parameter b. I know that the parameter b is 2, so the period of my function for number 1 should be 2 pi divided by the absolute value of 2, which is pi. So what that means is there will be a horizontal compression by a factor of 1/2 from the graph of the parent sine function. The parent sine function has a period of 2 pi. Our function has a period of pi. So we will take the green graph and horizontally compress that by a factor of 1/2, which means you're going to multiply each x coordinate on the green graph by 1/2. So the x coordinate of this point, 1/2 times pi over 2, will become pi over 4. The y coordinate stays the same. The x coordinate of this point will become half of pi, which is pi over 2. The y coordinate stays the same. The x coordinate of this point, half of 3 pi over 2, will become 3 pi over 4. The y coordinate stays the same. The x coordinate of this point, half of 2 pi, will become 1 pi. The y coordinate stays the same. So now I'm ready to go ahead and connect my 4 points. And this will give me the graph that you see in gold. So 2 things have happened already. We've had a vertical stretch by a factor of 2 and a horizontal compression by a factor of 3. So we've taken care of A and B. So now we go to C. The parameter C will give us a vertical translation. So now we will go ahead and take a look at the gold graph and take the y coordinate of each point on the gold graph and add 3 to it for the vertical translation upward by 3 units. So this point, which has a y coordinate of 0, will now have a y coordinate of 3. This point, which has a y coordinate of 2, will now have a y coordinate of 5. This point, which has a y coordinate of 0, will now have a y coordinate of 3. The point here with a y coordinate of -2 will now have a y coordinate of 1. And this point here with a y coordinate of 0, 0 plus 3 will give me 3. So now I will get my next graph, which I will go ahead and sketch in black. So this is what we have. But this is not the final graph because we've only taken care of 3 of the 4 parameters. The last parameter is D, which will give us a phase shift of pi over 8. So we're going to take the x coordinate of each point on the black graph and add pi over 8 to the x coordinate of each point. And when we do that, the first point, which has an x coordinate of 0, 0 plus pi over 8 will give me pi over 8. The y coordinate stays the same. So now we're taking care of the phase shift, and this is what we have for the phase shift. And our final graph will be the red graph. And it will be right here. And this red graph, if you look at the coordinates of the points on the red graph, they are pi over 8, 3, 3 pi over 8, 5, 5 pi over 8, 3, 7 pi over 8, 1, and 9 pi over 8, 3. And of course, this is the same thing that we got with our table. You can see we had pi over 8, 3, 3 pi over 8, 5, 5 pi over 8, 3, 7 pi over 8, 1, and we also had 9 pi over 8, 3. And you can see the red cycle from our sine graph, and that's the same thing that we just looked at, doing it a different way. So today we looked at objectives 1 and 2. You'll be able to sketch graphs of functions that are transformations of the parent sine and cosine functions. For a given graph of a transformed sine or cosine function, you'll be able to identify its amplitude, period, the equation of the midline axis, and the phase displacement. And you will also understand how the parameters a, b, c, and d affect each of the above. And we were able to look at 2 different ways you can sketch the graph of a given transformed sine function.